Yes. Hello viewers, welcome to my channel. So in the present class, now I am going to start the topic energy density in the stretched string. So for that, you consider a stretched string of length L, linear mass density mu, right sir? When the transverse wave is propagating in the stretched string, here the medium is nothing but the material of that string. The medium particle vibrates perpendicular to the direction of wave propagation. So here the string is along the x-axis, the wave is propagating along the positive x-axis, then the particles of the medium are vibrating along the y-axis. So here the particles are vibrating about their mean position. They are in the simple harmonic motion. Clear, sir? Now, so when the particles are vibrating perpendicular to the direction of wave propagation, the disturbance will carry from one particle to another particle. So that results crest and trough so alternatively. So in such a way, the transverse wave can advance in the string. Right, sir? So since the particle is in the simple harmonic motion about the mean position, right, about the mean position or equilibrium position, if the particle has the kinetic energy and also potential energy. So let us calculate the first kinetic energy expression, after that potential energy expression. From that, we will approach to derive the expression for kinetic energy density, next potential energy density, by adding these to the total energy density. That is nothing but total energy in the string per unit volume. That formula we will derive here. Okay, right, sir. So for that, you consider this diagram. So this is x-axis. Someone is talking, please in mute condition, right, sir? So this is the transverse wave, which is propagating along positive x-axis. Here the particle is vibrating like this. This is the mean position. So this is the mean position. About mean position, to and fro motion. About mean position, both sides to the mean position along the y-axis, the particles vibrate. Here the disturbance can propagate along the positive x-axis. Right, sir? Just keep this mind in your this figure in your mind. Then what we are going to approach, you observe. So let us consider a small element of length dx in the string with a linear density mu as shown in the figure. So that will be, this is the figure. In the total length, just we are taking the small length element dx, small part. So this is the wave. In the wave, we are taking the small length element, small segment of length dx. When the string is in the vibrating mode, so that dx can become as ds. So dx length will change as the dx arc shape, that gets the arc shape. So from the point A to B, this is the point B. So this is the dx will change into this arc shape. Okay. So here compulsory the string should be in the tension, right? String should be in the tension. Suppose the tension applied on the string, So that is I'm shown here. This is a pulley. The one end of the string is connected at one fixed end. The second end of the wire or string is passed over a pulley, and at that end we are suspending some load M. Right, sir? Then what is the load or tension in the string? Then tension in the string would be equal to M into G, the weight of this load. The weight of this load acting downwards, then the tension in the string T is equal to MC. So therefore, when the mass M is loaded at the end of string, the tension in the string applied will be equal to mg, that is T equal to mg. Since we are considering the small length element, at the two ends tension will be the same. At the first end A, the tension T. At the second end A tension, both are in opposite direction, they are equal. When you take the large length of the segment, large length of the string, large element, then T value varies, T changes. But we are taking very small segment in the total length of the string L, we are taking the small length element. So for that, at the two ends, tension will be the same. Here also tension T, at the second also tension T. Okay, sir. Now, it is making angle theta with horizontal. So resolving into two components, then horizontal component, you will get a T cos theta. Okay, and vertical component T sin theta. Here also same horizontal component T cos theta, the vertical component T sin theta. So this explanation we covered in the derivation of velocity of the transverse wave in the string. V equal to root of T by mu. In the derivation, we talk this discussion. So this horizontal components gets cancelled. Here T sin theta, here T sin of theta plus T theta. Right, from that we are taking the resultant force. From that, we derive the formula V equal to root of T by mu. Okay, the same concept we are taking, the same figure we are taking here, right, sir? So here T cos theta cancel. Just you concentrate at this point B. So what I am saying is the string of length dx changing into the length ds arc shape when the string is in the vibrating mode, right, sir? Vibrating mode. So when it is a dx, this is a dy. So you can consider it as a right angle triangle, almost right angle triangle. Of course, it is in arc shape. If you take it as like this, then from Pythagoras theorem, so what is the ds? ds square is equal dx square plus dy square. From that, ds is equal to under root dx square plus dy square, dx square plus dy square, right, sir? So this is the figure description, right? So keep these ideas in your mind. Now the kinetic energy of that small segment, kinetic energy equal to half mv square formula. We know that mu is the linear density. Linear density is nothing but what? Mass per unit length. Mass per unit length. But here we have taken dx length. Dx length. So for unit length, the mass mu, then what would be the mass of the length segment dx? How much? This is mu into dx. Hence, the mass of a small segment of length dx is equal to mu into dx. Now, the kinetic energy half mv square, half mu dx into velocity dou y by dou t. Displacement equation y of x equal to f a sine of omega t minus kx. What is the velocity? What is the displacement or the wave equation? What is the wave equation? Y equal to a sine of omega t minus kx. Right. So there y is the displacement. If you differentiate with respect time, dou y by dou t is velocity, sir. Dou y by dou t velocity. Half mv square, in that mass mu into dx, velocity dou y by dou t, v square. Therefore, here written square. Okay. So then kinetic energy per unit length. Kinetic energy per unit length equal to dk by dx. Dk by dx. So dx by writing this side mu by 2 dou y by dou t whole square. Dou y by dou t whole square. So this is kinetic energy per unit length. Similarly, let us derive the expression for potential energy per unit length. Potential energy per unit length. So in the previous figure, actually we consider the length dx. When the string is vibrating mode, that small length dx changing into the arc shape of length ds. So how much there is change in length? Length dx changing into the ds. So what is the change in length? ds minus dx. ds minus dx. What is the tension in the string? Capital T. So then potential energy expression is given by potential energy equal to tension into change in length. This is the formula. Tension capital T into change in length ds minus dx. ds minus dx. Okay. Now, ds minus dx is equal to, right, But ds is equal to square root of dx square plus dy square. Already I explained this one. This is equal to dx square plus dy square whole power of, in this dx is taking common, 1 plus dou y by dou x whole square whole power of. Followed? So this is how I am writing dx square plus dy square whole power of. So from this you take dx common, dx square taking common, since there is off, so left side you will get dx 1 plus dy square by dx square. So that can be written as dou y by dou x whole square whole power of. Okay, sir. Dou y by dou x whole square of. So then, so dx is equal to, we have written. Okay. Now, 1 plus dou y by dou x whole square. 1 plus dou y by dou x whole square whole power of is equal to 1 plus x whole power n form. From binomial theorem expansion, you take the first two terms, neglecting higher order terms. 1 plus x whole power n equal to first two terms, 1 plus nx. 1 plus nx. 1 plus 1 by 2 dou y by dou x whole square. 1 plus 1 by 2 dou y by dou x whole square. Right, sir? So this is you substitute in the text previous equation. ds is equal to dx 1 plus 1 by 2 dou y by dou x whole square plus and so on. This is equal to dx into 1 dx plus 1 by 2 dou y by dou x whole square dx. So bringing the dx left side, ds minus dx is equal 1 by 2 dou y by dou x whole square dx. Followed, sir. 1 plus dou y by dou x whole square whole power of, we are writing it as 1 plus 1 by 2 dou y by dou x whole square. How we are writing? 1 plus nx form. 1 plus, here power is 1 by 2 into where x is nothing but dou y by dou x whole square. But the ds is equal to dx into 1 plus dou y by dou x whole square whole power of. Instead of this, we are putting here. Now again, you multiply dx into the bracket. Dx into 1 dx plus dx 1 of dou y by dou x whole square dx. Then ds minus dx is equal 1 by 2 dou y by dou x whole square dx. Potential energy du equal to tension into ds minus dx. What formula we have? Potential energy of the string is equal tension in the string T into change in length ds minus dx. ds minus dx, what we got? 1 by 2 dou y by dou x whole square dx. So that is substituting here. Then du equal to T into this much, T by 2 dou y by dou x whole square dx. Right. Then potential energy per unit length du by dx. Du by dx is equal T by 2 dou y by dou x whole square. So therefore energy density is equal to potential energy per unit length plus kinetic energy per unit length. Potential energy per unit length plus kinetic energy per unit length. Potential energy per unit length already we got T by 2 dou y by dou x whole square plus this is kinetic energy per unit length. Now potential energy per unit length, so T by 2 dou y by dou x whole square. Kinetic energy per unit length we got mu by 2 dou y by dou t whole square. Okay. Then yes. So by adding these two, we got this expression. Okay, equation something, a running equation 3 or 4 you say. But actually, what is the displacement of transverse wave in the stretched string? Y equal to capital A sine of omega t minus kx, where A stands for amplitude, omega angular frequency, k propagation constant, y displacement. So if you know the displacement, you can calculate or you can find the velocity of the particle. Velocity v is given by dou y by dou t, the rate of change of displacement. So A constant, Sign differentiation cos omega t minus kx into d by dt of omega t omega. So therefore, velocity of the particle v is equal to a omega cos omega t minus kx, cos of omega t minus kx. Similarly, from the expression y equal to a sine of omega t minus kx, you differentiate that with respect to x. Then you will get dou y by dou x. Dou y by dou x is equal a constant. Sign differentiation there cos of omega t minus kx into d by dx of minus kx, you will get minus. Hence, we got minus k a cos of omega t minus kx. Why we are writing dou y by dou t, dou y by dou x? In the previous step, in the previous equation, there energy density equal to there dou y by dou t whole square term and dou y by dou x whole square term is there. Hence, for that purpose, we are writing the expression for dou y by dou t and dou y by dou x. Now substitute these two values in that expression, previous expression. Hence, kinetic energy per unit length equal to mu by 2 dou y by dou t whole square. Mu by 2 dou y by dou t we got a omega cos of omega t minus kx total whole square. That is omega square a square cos square omega t minus kx. But the average value of cos square theta value 1 by 2. So this comes in mathematics. So cos square theta average value 1 by 2. So instead of cos square omega t minus kx, you write 1 by 2. Then into 1 by 2 will get 1 by 4 omega square a square mu, or mu by 4 into omega square a square. Omega square a square. Similarly, yes, potential energy per unit length equal to capital T by 2 dou y by dou x whole square. Dou y by dou x, what we got? K minus k a cos of omega t minus kx. So dou y by dou x whole square becomes as k square a square cos square omega t minus kx. Again, cos square average value how much? 1 by 2. So then you will get t by 4 k square a square. Don't accept. T by 4 k square a square. Average kinetic energy per unit length mu by 4 omega square a square. Average potential energy per unit length T by 4 k square a square. Right. So then the total energy per unit length by adding these two, so here again this expression changing into omega terms. Yes, don't one is talking, the k is equal omega by v. Propagation constant k is equal omega by v. V equal omega by k. From that we are writing k equal omega by v. So hence k square equal omega square by v square. So putting this value here, so what we got? Velocity of the transverse wave under root capital T by mu. From that v square equal to capital T by mu. You substitute this value in this above equation. K square equal to omega square by v square, that is capital T by mu sir. Hence, the potential energy per unit length equal to T by 4 omega square mu a square by T. T cancel. Omega square a square mu by 4. Omega square a square mu by 4. Right. Therefore, the total energy per unit length or energy density equal to mu by 4 omega square a square plus mu by 4 a square omega square. So both are the same. Average kinetic energy per unit length mu by 4 omega square a square. Average potential energy per unit length same mu by 4 a square omega square. By adding these two, you will get mu by 2 a square omega square. So therefore, finally, what we got is the total energy density of the string mu into a square omega square by 2. But angular frequency omega equal to 2 pi into frequency 2 pi m. If you substitute that value, in this omega square equal to 4 pi square f square. So then finally uh, energy density is equal to 2 pi square f square a square. Okay, the total energy density of the string 1 by 2 mu omega square a square. Again, we are substituting omega equal to 2 pi f. So then we get 2 pi square f square a square mu. So this is the required expression for energy density of the string. Energy density of the string. Okay, energy density of the string. So in this